Hello and welcome to the Inference chapter, section 1, exact inference. Assume that we have either learned the following Bayesian network, for example, by structure learning, parameter learning, or that simply an expert has given it to us. So the question is, what can I do with this Bayesian network? And one of the things that we can do, or perhaps the most fundamental thing, is answering probabilistic inquiries. For example, here, how can we calculate the probability of difficulty breathing? Now, there can be several methods to answer this question, but we are particularly interested in a systematic way of doing things in this chapter, in this section. A little bit of recall, probabilistic inquiry. A conditional probabilistic inquiry consists of two parts. There is an evidence, a subset Z of random variables, and an assignment small letter z, as well as inquiry variables y of random variables. The task is to calculate the posterior conditional probability distribution over the events y given the observed variables z. So this is what we have. And we often drop this z equal to and just denote it with small letter z only. We can, of course, use the Bayes theorem and write it in this way, where we have the prior marginal distribution, Py, the probability before observing the evidence Z, the likelihood function, Pz conditional y, which is the probability of observed data, it's also conditional, and the normalizing factor, P of Z. Another way to compute this is using the joint distribution P, Y, and Z. We can just write it by definition. Conditional probability is written in this way. And how can we calculate P, Y, Z for a certain event Y? Well, if I have all of the variables in the Bayesian network, for example, X, I usually know how to calculate P of X, for example, by Bayesian network composition, decomposition. So I try to write this PYZ as a marginalization of PYZW, all of them together. This is basically X. I just marginalize out W, okay? And in the same way, I can get P of Z when I marginalize PY. Y. Okay, so these are the recalls back to a similar problem to the initial problem we introduced in this section. We want to find the probability that the person not wearing a mask, M0, will be infected with COVID, C1. So in this case, in view of PY condition on Z that we just introduced, our Y is C, Z is masking, and the one that is not included here in the probability W is social distancing. How can we calculate this? Well, it will be P of C1 condition on M0. By definition, we wrote it like this. And again, we tend to always turn this into the full joint distribution, so all the three variables. Once we do that, we need to marginalize these gray ones because they're not included here. And then we can factorize it, right? According to the Bayesian network, it will be P of M times P of D times P of C condition on M and D. Great, let's now see what happens if we add 3 more nodes. In this case, we're interested in P of B, as in the original example. So the exact probability is calculated from the joint distribution by marginalizing all the variables except for B, and this means we have to calculate this summation. Okay, so this is already factorized. Here we originally had the joint distribution of all of these variables. It is now factorized according to this Bayesian network, and this means that we have 2 to the power of 5 terms, right? Each for one of these summations, 5 marginalized variables, and each are binary. So the complexity increased exponentially with the number of nodes compared to the previous example. Now you may say, well, for example, this one is quite simple. I can simplify it. P of V condition and V does not appear anywhere else, and this will be just 1. And you may apply some other techniques or tricks here. But in general, this is what we get. In general, we have the so-called BNPR problem that is given a Bayesian network, how to compute the probability of a certain variable taking a certain value. And this problem appears to be Sharpe complete. So it can be computationally expensive or even intractable. So here's the bad news. But in any case, let's see how we can do things systematically. So let's just assume that the problem is tractable, meaning that we have small enough number of variables that we can actually perform this computation. We want to introduce the so-called variable elimination algorithm that deals with this problem algorithmically. And let's see how it works. So back to our example, we saw these many summations exist. We want to see how to perform them and possibly simplify them. Well, the idea is to first push the summations into the factors involving the corresponding variables. So here, for example, we have M first appearing, D, F, C, V. This is just a random order that we wrote the summation. And we start with M. So I push all the ones that have the variable M inside this summation. So here I see that the first one has it, and the third one has it. The other ones don't have it. So here I have with the first summation. Then I move to the next one, D. Which ones appear to have D? Here I have P of D. This one already appeared, and none of the other ones have it there. So I will have P of D appearing between M and D in the summation. Then I move to F. It's only this term. C, I'm moving according to this order. C, all the ones have appeared except for P of B condition on C, and the final one is V. Okay. Now note that this order is arbitrary and it can be different. Here we're just following the one appeared here. So I end up with this pushed summation, and now the calculations start from the inner summation. Okay, so I will start with this term. Okay, what should I do? So first, I will multiply the factors phi m and phi c, and which are defined here. So I call the term that includes only m phi m of m, and this one is phi c. This is my notation that I will use here. It's phi c because c is appearing on the left-hand side of the conditioning, and all the variables then are listed here. Okay, so I first have to multiply these two, and how I can do that is just looking at the probability table. So P of C condition on M and D is this term here, right? The values of C, the CPD, and the M and D are appearing here, and this needs to be multiplied by P of M, which only takes two values, M0 and M1, and I need to multiply them. So the way I should do this, according to this table, is straightforward. The first two rows have M0, so I need to multiply them by P of M0. And if you have a look back at the table, you see that P of M was 1/3, 2/3, and the other table that we're looking at is this one. Okay, so if I go back, so I have this table over here. I'm just multiplying the first two rows by these numbers, and the last two rows by these ones. So if I do this, then I can marginalize M. That's basically what I'm doing in this first inner summation. And then I will end up with this table, which I denote by this notation like tau 1 of C and D, because it only depends on C and D, M is over. And look the shape of it. So C0, C1 still are appearing here as before. D1, D0 are also appearing as before on the left-hand side of the table. It's just that M0 disappeared. Okay, so again, we multiplied this row by 1/3 and this one by 1/3 and added them up. And if we do this, we will end up with these numbers. Okay, great. What's next? So this gives us this new factorization over, and by the way, we call it a scope. This part, CMD, this is the scope of this function of, or this factor phi. And here CD is the scope. The next is to marginalize the D variable from the second summation. So now I have P of D, I have this tau 1 of C and D, and this is really my factor phi of D if I'm treating it as, defining it in the same way as before. So I just need to multiply these two. And how does that happen? Well, I will again write down tau 1 here. It's easier to have the table first written, and then I will just multiply it by the values that P of D take. Here the phi D is just D0, D1. We can look it up, and these are the values. So same as before, we marginalize D, and we will end up with a table of single row, which is the values of C. Okay? So this new factor has the scope of only C, and it goes before the summation. Okay? So if you just compare these two, I will have P of F condition on C, and I should put really tau 2 of C that I just calculated here, so it should really appear here, but I can actually push it backwards because it doesn't depend on F, so I don't need to do the calculation here, and I will push it one step further back. Now, why is this helpful? Well, because here, now I have a probability that on the left side of the conditioning, I have exactly the variable that's going to be marginalized out, and this means that this is simply 1. Okay? C is considered fixed in this summation, adding over the probabilities of F, which is 1, and even if we wanted to do it in the systematic way, we would have put this factor here, and I'm marginalizing F, but I don't have really another factor to multiply it. So I will have to put like F0 here. If I wanted to multiply this time, I had to multiply over the columns, right? Like, doesn't matter whatever value of F0 here I have, and then whatever value for F1 I have, I don't have anything else to multiply by. So I just need to add these columns, and they add up to 1. Okay, great. So it's basically 1, and I can still keep it here, or I can just remove it. So again, since when we're doing things in a systematic way, let's assume that we want to keep it in the general form, and we just put it here as it's defined. The fourth step is to redo the whole thing for C, and that means I have to multiply this factor into tau 2 of C into tau 3 of C. Tau 3 of C has no effect here. I just need to multiply this by C in the same way as before. I marginalize C out, and this will be the result. So the final step is now to take out V from here, and this again we can write down in this way. Now again, note that tau 4 of B can be pushed out of the summation because it doesn't depend on V, and this again makes this summation equal to 1. We already saw that in the beginning, right? We said that this summation can be made to be equal to 1. So at the end, I just end up with these two factors, and if I multiply that, then I will get this final result. Okay. Using this variable elimination method, we only use 36 multiplications and additions. Now, can I use this method to find a conditional probability? What I did previously was just P of B. For example, what if I want to know P of C condition on M0 and F1, a probability of a person being infected with COVID, given that the person did not wear a mask and had a fever. Okay, by definition, it will be this fraction, and the denominator can be calculated from the numerator by just marginalizing c. So we will focus on just the numerator for now. The question is, how can I use this information of conditioning on M and F? So I know that the person was not wearing a mask but had fever. So this basically means that in the CPDs, I don't care about the other possibilities. So I can just leave out M1 in all the CPDs as well as F0. Okay, I just cross them out. And this simplifies the tables when I'm doing the calculations multiplying the factors. Okay, so if I write down the factorization, this time it's a different order, and it's still the joint probability distribution, and you can see that I no longer have summation over M or F because I know the values. I don't want to marginalize them. So I only end up with 3 summations. So I will continue it in the same way as before. So these are the factors, and you can see that in the factors now M does not appear, right? Because the value is known, same as here, as well as F. Okay. So the first step is to eliminate V, and I know this is 1. If we want to do it, we can still do it, and we see that we just need to add up these 2 possibilities. They add up to 1. So that will end up with tau 1 of B, okay, and this can be pushed, well, this can now be just multiplied in this PB condition on C. I already know this is 1, so if I do that, I will end up with, again, the value of 1, because this is 1, this is P of B condition on C. C is assumed constant in this summation, so I will end up with 1. And this will be just tau 2 of C, because B is marginalized. Now this tau 2 of C can be pushed back of this summation. It is 1, it doesn't matter. But again, doing it systematically, I will just push it back, and the only thing I need to do is this calculation. Right, these 2 factors. Now look here, phi C of C and D, M does not appear. Okay, so it's simplified. But the way of doing it is same as before. So I have this row, I need to multiply it by 1/3 and 2/3 for the second one. Okay, and then I will add them up. So I will end up with this. Can continue on. The last term will be here. So that ended up to be tau 3 of C. Now I have to multiply all of these ones. So the first one is just 1/3 because it was just M0, and the probability of M0 is 1/3. I wrote down the second, the third, and the fourth. If you do the math, this is what you will end up with. So by marginalizing C, which I need for the denominator, then I will get this summation. Okay, this probability is 0.3, which you can see by adding these 2 columns. So the fraction that I was looking for is this, and it, depending on the value of C, I can have either of these 2 probabilities. So if we want to know the person is infected, it will be 83%. Otherwise, it's 17%. Perfect. So back to our complexity problem, we saw that, well, yes, answering this problem, BNPR, computing a probability of a variable in a given Bayesian network, this is short P complete. So quite difficult and often infeasible, intractable. So what about approximations? Okay, so what kind of approximations are we interested in? One is a relative error. So an estimate delta hat has relative error epsilon for delta. So this is assumed to be estimating delta. That's why it has a hat. If the fraction of delta divided by its estimate is bounded from above by 1 plus epsilon. So it exceeds 1 by at most epsilon, and it doesn't fall short of 1 over 1 plus epsilon. Okay. Then we say that this estimate delta hat has relative error of epsilon. Okay, so what if we want to obtain delta hat? We know that finding the exact value of this probability is sharp p-complete. So maybe it's easier for this delta hat, but then even finding a relative error, an estimate with a relative error of epsilon, I will give you the epsilon and say find some estimate bounded by epsilon. Still, this query is NP hard. So kind of bad news again. What about another type of error? So absolute error. An estimate delta hat, this time we say that it has an absolute error of epsilon for delta if the difference is bounded by epsilon. Quite intuitive. What about this case? Well, the problem of approximating p of x with an absolute error of epsilon has a randomized polynomial time algorithm. This is a good news. It's just that if an evident is added, say E or Z, then it again becomes NP hard. Okay, so a mixture of, I would say, good and bad news, but we learn how to do things systematically, and if we're interested in approximations, these are the complexity. So obtaining exact posterior distribution, like conditional probabilities, this can be computationally intractable or expensive, NP hard. Approximate inference algorithms approximate posterior probabilities and are generally orders of magnitude faster than explicitly manipulating the joint distribution, but still they can be NP hard. So there is a trade-off between computation time and accuracy. And this is quite common, not just in Bayesian networks. Okay. The type of approximate inference that we're interested in is the particle-based approximate inference, which we will explore in the next sections. Thank you.